Hello everyone, it's Mr. Canfield. Today we're looking at function analysis. So, it sounds scarier than it is. We're basically going to be going, hey, what's the derivative do? So, here's some generic function. And we can see that the function, if we kind of look from left to right, we could say, oh yeah, the y values of this function are going down. The word for that we use is decreasing. When it's flat, we call that constant, and when it's going up, we call that increasing. So hopefully, if you've never thought about things in terms of those words before, hopefully that's not that big of a deal. Now, there's a really flashy way for us to talk about it. So the definition of increasing is if x2 is greater than x1, and so like the second x is further along than the first x. And then the second y value is bigger than the first y value. So a function is increasing if a y value is bigger as you go on, and decreasing the other way around. Now, notice how it's greater than or equal to. So we could say we could talk about increasing from a to infinity. We don't really use this line of discussion though. We would generally really talk about increasing from b to infinity, but then we have strictly increasing. This is like the more what you would think of as actually increasing. So we could say, sure, it's increasing from here to here. We would call this monotonically increasing is another way we talk about it, where it's either staying flat or going up. And so I'm generally going to use the word monotonic to remind you that there's the possibility it's going flat. And strictly increasing, I'm usually going to refer to just as increasing. So these are subtle details that are not super important. So here, like in this function right here, we can see it's increasing flat and then still increasing. So we would call it increasing along this whole way. I would say this is monotonically increasing. This isn't something I'm going to be testing you on. I just want to make sure my terms are clear. And this, we'd call this strictly increasing. It has no places where it's completely flat for longer than a point. So right here, the derivative actually would be 0 and it'd be flat, but not the biggest fan of how Stu talks about this. I think we could have some better examples, but let's move on. So if you were to calculate the slopes here, and remember, slope and derivative are very closely related. So if I was to look at the slopes of each of these tangent lines, we'd see that these are all positive slopes. So we would call this an increasing function. Similarly, if you look at the slopes of the tangent lines here, these are all positive slopes, and so we would say that the slope of the tangent line is positive, or the derivative is positive. Similarly, oh wow, look at that, the slopes are still all positive. So slopes of tangent lines of increasing curves are always positive. And I think the really important thing to remember here is that a positive slope in the picture means that f prime is a positive number. So like if I got that f prime was equal to 2, that would literally mean that the slope at that point was rise 2, run 1. Like the slope would be like that. So anytime we get a positive number out for a derivative, it's in a positive slope, which means the function f of x is actually increasing. So then we look similarly, we look at these functions, and if we did the same thing drawing those tangent lines, we'd see that these are all decreasing functions, which, you probably realized that before I went through and was like, oh, look at that, the tangent lines go down. Yeah, surprise, the tangent lines are falling from left to right. Whoa! So we should notice then that a decreasing function has a negative slope, and so the f prime is going to be negative. So if we want fancy language for this that we're eventually going to need to use in some way, shape, or form, if f prime is greater than 0 on an interval, then that means that f is increasing. Notice how f prime influences f. F prime tells us things about f. So here it says f prime greater than 0. What does that mean? That means that the derivative is greater than 0. No matter what x I plug in, I get a number more than 0 between a and b. And then similarly, so between A and B, so I got distracted. If the derivative, plug in any x for the derivative, and it's greater than 0 between A and B, then that means that for every single x value in between A and B, the actual y values are going to be increasing. So we're going to see that the derivative affects the original function. F prime always affects f. Similarly, f double prime is going to affect f prime, which is then going to affect f. We'll talk about that more later. So the same kind of thing happens where f prime is negative, therefore f is decreasing. If f prime equals 0, then we would say that f is constant on an interval. So notice how he's switching back and forth between using these brackets. These are all on the AP exam. These are all interchangeable. They do not make a distinction. So no matter how you write your parentheses or brackets, it's acceptable. I'm going to stick to essentially writing parentheses in this class just to avoid any extra confusion. There is subtle changes that we can make to the parentheses and brackets to subtly change what things mean. But in the context of this course, we're going to say it doesn't matter. Okay. He uses the term critical value. This is the first time I've ever heard it called critical value. I grew up calling them critical points. An old textbook I used called them critical numbers. So here, and I'll put an S on. Critical values, critical points, critical numbers. We're going to use these three words interchangeably. And all they are is when f prime is 0. Or when f prime is undefined or does not exist. So if I wanted to find the critical values, see, I'm using his word now. If I want to find the critical points of this, all I got to do is we'll find f prime and say, okay, well, f prime is going to be 12x minus 3x squared. And then if I want to find the critical points to that, I'll just set it equal to 0 and solve. So I'll factor a 3x out of that, and I get 4 minus x. And so I get that x is equal to 0, and x is equal to 4. And you might remember this from when we were talking about physics stuff. These would be like the peaks and troughs of our projectile motion problem, or the highest or lowest points that they might reach. And in general, we're going to use these as a way of finding when a function is increasing and when a function is decreasing, because when x equals 0, f prime is 0. And remember, when f prime is 0, that means the original f is constant. So if I were to have more space, which I don't, so if we look here, and we look at this as a sign chart, so let's see, I've got my 3x and I've got my 4 minus x. So I know I'm going to deal with 0, and then I'm going to deal with 4. We want to see what happens to f prime. So what's going on with f prime? So pick a number less than 0. I'm going to pick -1, why not? So I get a negative here, I get a positive here. That means f prime is negative, because a negative times a positive is a negative. Then I'll plug in 0, and I get 0, and who cares, so I get 0. Here, same thing, I plug in 4, and I get 0 there. So pick a number between, I'll pick 1. So I get a positive here, I get a positive here. That means f prime is positive. And then pick a number after 4, and I'll pick, I don't know, 5. So I get a positive here, I get a positive here, and then I get a positive here. I was not expecting that. Oh, nope, okay. I was expecting alternating, because oftentimes they do in polynomials, and I made a mistake, right? Because 3 times 5 is 15, 4 minus 5 is -1, so that's going to be a negative there. So I'm going to change this to a negative. Let's think about, what does this do to f of x then? Well, it says f prime is negative, so which way is f of x going? F of x is falling, right? Now flat means it's flat here. Positive means it's going up, right? If a slope is positive, it means f is going up, and then flat again. Negative means it's going down again. So we actually could kind of visualize this on a kind of, some people like to call this a wiggle graph. You know, we're wiggling down. We don't know exactly how, but it's going down, flat, up, flat, down. Does it ever flatten out again over this way? And the answer is no, because the only way it could ever flatten out is if the derivative is equal to 0. And so that is going to lead us into our next discussion of how we figure out relative maxes and mins, but I don't have enough time to do that right now. So I'm going to do one more example in the time that I have left. Actually, no, I don't have time. So hope this was helpful. I will try to get another one as fast as possible. So yeah, I already said that hope this was helpful. I still actually do hope this was helpful at this point in time as well. Bye.